Hello, my name is Aral Sarrafi. I'm a PhD candidate at the University of Massachusetts, and I would like to present my work on simulation of a lane keeping assist system for self-driving cars in MATLAB Simulink. The self-driving car industry is predicted to be growing by 42% within the next 4 years. This project is mainly focused on using the principles of computer vision and control to design a lane keeping assist system for a self-driving car in MATLAB Simulink environment. In this work, I will be using only the camera data and a computer vision toolbox in MATLAB Simulink environment to process the acquired sequence of images. The camera mounted in front of the vehicle will be used to generate a desired steering angle for the self-driving car to keep the vehicle in between the lane lines. The sequence of images will be analyzed in the perception unit to estimate the deviation of the vehicle from the center of the road. This error signal will be used by a PID controller to generate the desired steering rate for the front wheels. For this simulation, a virtual reality environment consisting of a driving track and a vehicle with a mounted camera in front is designed using the 3D animation module. This is a driving track environment, and this is our self-driving car. It is not a fancy car, but it will do the job for our simulation. And this is the field of view of the camera mounted on top of the vehicle. The sequence of images captured from the camera is given to the perception unit in the simulation to detect the lane lines. So let's take a closer look at the components of the perception unit. First, the perception unit converts the captured images from the camera to the HSV color space. Normally, the printed lane lines on the road have high saturation values. Therefore, applying a threshold on the S channel in HSV color space can isolate the lane lines. This threshold stage will generate a binary image representing the pixels associated with the lane lines. In general, processing the binary image to detect the curved lane lines in the camera coordinate system is not straightforward. Therefore, the images will be transformed using a projective transformation to obtain a bird's eye view of the scene. The bird's eye view will transform the image as if the camera was flying over the car while facing the ground. The bird's eye view binary image is then passed to the lane detection unit. The lane detection unit is a point cloud processing unit implemented in a MATLAB user-defined function in Simulink, which detects the lane lines and fit a polynomial to them. The lane detection unit also estimates the deviation of the vehicle from the center of the lanes, namely the error signal. The center of the road can be estimated by averaging the intersection points of the left and right lanes with the x-axis, namely x left and x right. Assuming that the camera is mounted in the middle of the vehicle, the error signal can be computed by subtracting the location of the camera from the center of the road. The PID controller uses the feedback from the perception unit to generate the desired steering rate as the control signal for the vehicle. This control signal will be passed to the vehicle dynamics unit to update the states of the vehicle. The nonlinear dynamics of the vehicle is implemented in a MATLAB user-defined function combined with an integrator. Once the states of the vehicle are updated with respect to the control signal and the previous states, the states vector will be passed to a simple signal processing unit to prepare the signals to be compatible with the virtual reality environment. And finally, these Simulink signals are used to drive the vehicle in the Simulink 3D animation environment. Okay, let's take a look at the final results. As it is clear, the vehicle can merge to the track and stabilize itself to maintain in between the lane lines. And as the curvature of the road changes, the controller can generate the correct control signal for the front wheels to keep the vehicle in between the lines. The project is a standalone and only requires MATLAB and Computer Vision Toolbox. A C compiler is also required to set up the MEX configuration to be able to use the user-defined functions in Simulink. All the required files for this set of simulation can be found in the link in the descriptions. Thanks for watching. My name is Aral Sarrafi, and this is my contribution to the Simulink Student Challenge 2018.